This is lesson 49 on subtractors. You remember in lesson 45 we designed a full adder from two half adders. Let's do the same thing in this lesson for subtractors. Here's the truth table for a half subtractor. The difference D is going to be A minus B, and C is going to be the borrow. So 0 minus 0 is 0 with no borrow. Let's skip this one. 1 minus 0 is 1 with no borrow. 1 minus 1 is 0 with no borrow. What about 0 minus 1? Well, 0 minus 1, we need to go to the next column and borrow a 1. Well, in binary, when you borrow a 1, you're really borrowing a 2. So what we have here really is 2 minus 1 is 1. So 0 minus 1 is 1 with a borrow. So look at D0. 0, 1, 1, 1 is just an exclusive OR. Well, that's just what we had for a half adder, you remember. So the difference, D, A minus B, is exactly the same as the half adder, A plus B. But there's a difference in the borrow. Remember, for a half adder, we had an AND gate here, 0, 0, 0, 1. But now we have a 0, 1, 0, 0, which means that C1, that is the output borrow, is just the minterm not A and B. So we need to put a bubble here indicating a not. So this is not A and B. So this will be a symbol for a not A and B, which would give us the borrow of a half subtractor. Let's try subtracting two 4-bit numbers. That is, we're going to subtract B from A. A is 5, B is 7. So let's do this subtraction. 1 minus 1 is 0. There's no borrow. 0 minus 1, remember that's just 1 and a borrow. 1 minus 1 is 0. Minus 1 is another 1 and a borrow. And 0 minus 0 is 0. Minus 1 is another 1 and a borrow. So here we had 5 minus 7, which is really minus 2. This 1, 1, 1, 0. If you take the 2's complement, you get a 2. So this is really minus 2. And we have a borrow indicating that the 5 is really less than the 7. So in general, we're going to be taking AI, subtracting BI. You have a borrow in general, and then you subtract CI. So the difference DI is A minus B minus the borrow, and in general you'll have a CI plus 1 borrow out. Well, let's look at the truth table for a full subtractor. The half subtractor was the borrow in is 0. We had that before. Let's see what we have here. We have 0 minus 0 minus 1. That's 1 and a borrow. 0 minus 1 is 1 and a borrow minus 1 gives 0 and a borrow. 1 minus 0 is 1. Minus 1 is 0 and no borrow. 1 minus 1 is 0. Minus 1 is 1 and a borrow. So this is the truth table for a full subtractor. Notice the difference. D has the minterms 1, 2, 4, and 7, exactly the same as a full adder. And remember, we showed for a full adder that the sum was just C, the carry in that case, in this case the borrow, exclusive ORed with A, exclusive ORed with B, with C in. So DI is going to be exactly the same as SI for the full adder. If we look at the borrow, the CI plus 1, for the full subtractor, it's a little different than the full adder. Here we have minterms 1, 4, 5, and 7. 1, 4, 5, and 7. So here we in general would have 3 circles, but let's do the same thing we did for the full adder. That is, take these min terms and see if we can simplify it using some Boolean algebra. This one is just going to be not A and B, and then here we'll just have the min term C and not A and not B, and here we'll have C and A and B. And now let's notice that we can have a common C that we can factor out here. So Ci plus 1 is going to be not A and B, or C and not A and not B, or A and B. And you should recognize that now as a exclusive NOR. So this is going to be not A and B, or C and this bracket is just A exclusive OR with B not. So it's exclusive NOR, and you recall that the difference is the same as the sum of a full adder, and so we have these two equations for a full subtractor, and from that we can draw the logic equation. The top just looks like a full adder. The difference is just C exclusive ORed with A exclusive ORed with B. That gives D. And Ci plus 1, the output borrow, is just, we need a bubble here, not A and B, ORed with C, ANDed with not A exclusive ORed with B. So this bubble would be this not here. And you should recognize that as the half subtractor that we had. And here's another half subtractor. So just like the full adder, we can make this full subtractor out of two half subtractors, plus this OR gate here. So look at the difference between the half adder and the half subtractor. Notice the only difference is this bubble. Well, the bubble, we can use an exclusive OR gate here remember, exclusive OR gate we can use as a controlled inverter. So if we make E equals 0, we want to get this picture. We want E equals 1 to get this picture. So here's how we can make an adder subtractor in one circuit. This is the bubble, sort of a controlled bubble. So if we bring in E here, then when E is 0, then A gets through. E is 0, A gets through. So this is just a full adder. But if we let E equal 1, this becomes an inverter. This becomes an inverter, or a bubble in this case. And so the output is a full subtractor. So here we have an adder subtractor that we can control by E. Now, here is the truth table for a full adder. Now what I'm going to do is I'm just going to rearrange the order of these entries. Normally in a truth table we go 0, 1, 2, 3, 4, 5, 6, 7, but there's no reason you have to do that. In fact, let's start with this 5, 1, 0, 1, and this is 0, 1. And now let's take the 4. So take this line and move it up to here. Then let's look at 1, 1, 1, 1, 1. We move that up to here. So I'm just shuffling these lines, not changing anything, still a full adder. Let's do 1, 1, 1, 0. So this line comes up here. Now let's take this 1, 0, 0, 1, 1, 0. Put that right there. Let's take the first one, all zeros. We'll move to here. And we got two more. We'll take the 3, move it down to here. And finally we'll take the 2 from here and move it down to here. So I've just shuffled all these rows to make a different version of a full adder. So this is clearly the truth table for a full adder. Now let's draw the truth table for the full subtractor that we had earlier. So here's the full subtractor, and I want to compare this full subtractor with this full adder. Let's look at the first column, C. Here's 1, 1, 1, 1, 0, 0, 0, 0. Here's 0, 0, 0, 0, 1, 1, 1, 1. So you notice that this column is just the naught of that column. How about the A? 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1. Those are exactly the same. How about the B? Here I have a 1, 0, 1, 0, 1, 0, 1, 0. But here I have a 0, 1, 0, 1, 0, 1, 0, 1. So that, again, is the naught. So this B is just the naught of this column. How about the S and the D? Well, they're identical. How about CI plus 1 and CI plus 1 here? Here's 1, 0, 1, 1. This is 0, 1, 0, 0. And this is 0, 0, 1, 1, 1, 1, 0, 1. So again, this is just the naught of that column. So the CI, the full subtractor, the CI, the CIN, is just the naught of the CIN for a full adder. The B is just the naught of the BIN for the full adder. And the Cout is just the naught of the Cout. What does this mean? Well, it means that we can make a full subtractor from a full adder if we just remember to put bubbles here. So if I have a bubble here, that knots the B, a bubble here knots the C in, a bubble here knots the C out, the D is the same, the A is the same. So here is clearly a full subtractor made from a full adder. Well, let's look at how we might do this with a 4-bit one. Remember, we need a bubble on the B. Well, I can get the bubble on the B by making E 1. So what I'm going to do, if E is 0, this is just no bubble here, and the carry just comes in, and it looks exactly like a full adder. So clearly, if I set E equal to 1, this is a 4-bit adder. But what happens when I set E to 1? Well, I set E to 1, this is a bubble. Well, that works. But remember, for a subtractor, I needed to have a bubble here. Well, if I make E 1 and it goes through the bubble, that makes it 0, so that brings in a 0 borrow to begin with. So that's good for a full subtractor. But the only other thing is we had a bubble out here and a bubble in here. But a bubble goes away, so that's okay. A bubble here and a bubble here goes away, that's okay. A bubble here and a bubble here goes away, that's okay. But I should have a bubble here. So here, I can think of this as being a full subtractor if E equals 1. The only thing I have to remember is there should be a bubble here. So if I get a carry out here, it means there really was not a borrow. But if I don't get a carry out, it means there really was a borrow. So the borrow is sort of the not carry out. So if I just remember that, then I can treat this full adder as a full subtractor by just making E equals 1. Now, let's look at it in a little different way. Suppose I make E equals 1 here. Let's see what happens. If E is 1, this makes this an inverter, but inverting all the bits of B is the same as taking the 1's complement of B. So this full adder here means take the 1's complement of B and add 1 because I have a 1 coming in this full adder. But the 1's complement of B plus 1 is just the 2's complement. So what I'm really doing here is adding A to the 2's complement of B. But you remember that the 2's complement of B is just minus B. So what I'm really doing, D, this difference out here, is just the sum of A plus the negative of B, because I take the negative of B by taking its 2's complement, and this bubble takes the 1's complement, and the E coming in here adds the 1. So I'm really taking the sum of A plus the 2's complement of B to get the difference D. That, in fact, is how subtraction is done in most microprocessors and things. You really don't need to have a subtractor. The way subtraction is done is by taking the 2's complement of what you want to subtract and adding it to D. So D is just A minus B.